Hello, everybody. This is lesson 3 in Math 100. Okay? Lesson 3 has to do with an if-then statement, or otherwise called a conditional statement. And also, it has a lot to do with induction versus deduction. These are the two types of arguments. We'll be focusing on deduction. And then we will be checking for what is called the validity of a deductive argument. It's a fairly important topic in chapter 1, so I hope you will get that and then pay close attention to all the details. All right, so here we go. All right, so here's the handout for lesson 3. I hope you have a blank handout in front of you. So go ahead and write down the title or the topics, deduction or induction and deduction, okay? So as I mentioned, these are the two main types of arguments. Some arguments are deductive, many arguments are inductive. Basically speaking, inductive arguments are what you'll see in sciences, okay? And basically in everyday life. It's basically patterns. You know, when you feel something over and over again, then you think that that's the general statement. Deduction, on the other hand, is more mathematical, and this is logical, mathematical, and that is what we will be focusing on here, since, well, partly because this is a math class. So the main question is, how do you determine and here's the key word, okay, for today, validity. It has nothing to do with the patterns, so to speak. It really doesn't have much to do with the truth either, okay? So it's really about the form of the argument itself. And it's been studied ever since the times of Plato and Aristotle and other Greek philosophers. So this goes way back, and you may have studied this perhaps as a part of your English class, or maybe even a speech or communications class, as well as in your philosophy class, such as formal logic. All right, so our focus here, again, we focus on the validity of deductive argument. So what do I mean by induction and deduction, or inductive and deductive argument? Right. So first we have a sort of a typical way we come up with our conclusion. That's called a deductive argument, right? So based on specific cases, you make a general conclusion. So the key here is to go from specific cases to general, right? This is called generalization, right? Have you heard of that? Yes, of course. Okay, this is how we, as humans, or maybe even animals, come up with conclusions. I say animals because this is pretty clear that animals do have inductive argument skills, right? So you feed a dog every day at a certain time and certain hour, or you just provide a certain bowl. You may have pets. And by the way, thank you for your reply or feedback in the first assignment, because now I know that many of you have pets. Many of you live with animals. Some of you even calling your sisters and brothers animals that you live with. I am not sure if that's a compliment, probably not. But anyway, an inductive argument is based on specifics and then come up with general conclusion, okay? So if you feed a dog at a certain time using a certain bowl, or in Pavlov's case, you ring a bell before you feed the dog each time. And after a while, just hearing the bell makes the dog to salivate. And so that's called an inductive argument. You hear or you experience over and over some specific instances, and then you make a general conclusion, okay? So here's an example of it. Sparrows fly, doves fly, eagles fly. Therefore, and you may conclude all birds fly. Right? And people use this kind of argument all the time. I got better by taking this medicine. Yeah, and he got better by taking this medicine. She got better by taking this medicine. See, everybody gets better by taking this medicine. Oh, that's dangerous, isn't it? Yeah, so inductive arguments don't always work, but that's how we make general conclusions. On the other hand, we have what we call deductive arguments. What is a deductive argument? Okay, this is the opposite. So you have some general rule or general rules, and then you apply them to make specific conclusions. So the argument goes pretty much in the opposite direction. You have a general statement, sometimes called a theorem or an axiom or a postulate, and then from there, you apply that specific or a general argument, general rule into a specific case, and you make your conclusion. All right. So here's an example. Everybody must have a student ID card, or every student must have an ID card. You are a student, and therefore, what's the conclusion? You must have an ID card. You see that? Now, this is actually a true statement. And in fact, this is called a valid argument. Every student must have an ID card, okay? You are a student. Because every student must have an ID card and you are a student, the conclusion is, and this is a valid conclusion, you must have an ID card, okay? You may say, what happens if I'm not a student? You know, if this whole statement is a lie? Well, okay, so that's still valid, but it is not sound. And so we'll talk about the difference between a sound argument and a valid argument later. Okay, so you check for strengths and weakness of an inductive argument. Okay, so remember here I said sparrows fly, doves fly, eagles fly. And you can even say crows fly and pigeons fly, and therefore all birds fly. Is that a strong argument? It's not really a strong argument, because you can see, you can probably come up with a few counter examples, right? Like chickens. How about other birds that don't fly? You know that, well, you know probably a few other birds that don't fly. And so, so this is not a strong argument here. Okay, so you check for the strength and weaknesses of an inductive argument. But you don't do the same thing. You don't talk about strong or weak deductive arguments. You check for the validity of a deductive argument. Okay, so that's the difference between inductive and deductive argument. I was trying to remember the animals, the birds that don't fly. And what I was thinking about is penguins, okay? And it turns out penguins are birds, and you have probably never seen the penguins fly. And so it's not true to say all birds fly, okay? But I mean, generally you can say many or most birds fly, right? So that would be a good inductive argument. It's just you cannot say all birds fly based on a few cases, because there are counterexamples. And so, but that's not the case with deductive arguments, okay? So deductive arguments are not strong or weak. They are basically, you know, black and white. It's basically valid or invalid. And there's a clear system of figuring out when a deductive argument is valid. Okay, so one of the most important aspects or an ideas or an elements of deductive arguments is this conditional statement. Okay, basically everything in mathematics and many things in life are written in the form of a conditional statement. Remember what a conditional statement is? We did the truth table in the previous lecture. If P, then Q. And here's a notation. This is a generally accepted universal notation for if P, then Q. Okay, basically it says P implies Q, or P is sufficient for Q. Or you can also say Q is implied by P, or P implies Q, or how else do you say that? Q is a necessary consequence for P. There are all kinds of ways to read this, okay? Now, because I don't want to say everything in abstract, it's much easier to understand this in the context of an example. So here's my example. Now, I think this is a great example. You want to keep this example in mind. If you live in California, you live in the United States, okay? Now, this happens to be a true conditional statement, partly because California, or mainly because California is one of the United States, at least for now, right? Okay, so let's write down the three related or three statements related to this. Okay, so the example statement of a conditional is if you live in California, then you live in the US. You live in California happens to be the P part. You live in the United States happens to be the Q part here, all right? So based on this, we can come up with 3 additional conditional statements. Number 1, converse. Okay, the converse is obtained when you switch P and Q. So this will say Q implies P. All right, do you think you can write this? Yeah, and you should just be able to write this, and maybe you can pause this and try to write these things. If you what? By the way, you will always want to start the sentence with if. Okay, if something, then something. Now, technically in English, you can reverse this, right? I mean, you can say exactly the same thing here by saying you live in the US if you live in California. Okay, but that will get really confusing in studying logic. So whenever you write a conditional statement, you would always want to write your statement in starting with the word if. So the conditional statement, if, should come first. And then the consequent part, Q, should come later after the comma, okay? The first part is called a conditional clause. The second part is called the main clause in your English class. But the converse will switch the order of P and Q, not the if and then. You still start the sentence with the word if. If you what? Live in the US, then you live in California. Now you say, well, something's wrong with that because that's not true. Exactly, okay? So what I'm saying here is that even if the conditional statement is true, the converse may not be true, okay? The converse is not equivalent logically to the original statement. Inverse, the inverse is when you negate. Inverse is obtained by negating each part of the original statement without changing the order. Okay, so this time we are not going to change the order. So that means if you, and you negate this first part, if you don't live in California, then you don't live in the US. All right, now if you're paying attention to the form, you know, this is great. Yeah, and the inverse, you just negate both, right? Negation of P implies the negation of Q. And then if you come back to real world of California and the United States, again, you see something wrong. Because if somebody says this, you say, well, that's clearly not true, right? If you don't live in California, then, oh, you don't live in the United States. The residents of the other 49 states would be offended. For the same reason, they may be offended for the first statement. If you live in the US, then you live in California. That's not true. Okay, so the converse is not equivalent to the original statement, and neither is the inverse. Now, the contrapositive is the statement obtained by doing both. Okay, so the first one you switch, second one you negate it. This time you negate and switch. So this will say, if not Q, then not P. Okay, now this may be like really complicated to some of you. This may be really easy for some of you. You know, it depends on how logically minded you are. Some of you are and some of you aren't. But this is not too bad, okay? So try to understand all of these variations. The contrapositive of the statement would say, if you what? Don't live in, remember it's a negation of Q. So it's, if you don't live in the United States, then you don't live in California. Okay, so in other words, this would be saying if you don't live in the US, then you don't live in California. Now that happens to be true, by the way, right? Because if you don't live in these 50 states, there's no way you can be living in one of them. And again, the reason this is true is because California, precisely because California is part of the United States. All right, so here's a summary. The converse and the inverse. Now remember, these are not equivalent to the original statement, but they are actually equivalent to each other. Remember, they are both false in this context, precisely because California is not the only state, right? So the converse, if you live in the US, you live in California. And that's not true because there are 49 states. The inverse will say, oh, if you don't live in California, then you are not living in America. You're not living in the US. And people say that's not true precisely because of the same reason that you don't, there are 49 other states. So they turned that out to be logically equivalent to each other, okay? And then the conditional, the original statement. And I want to emphasize the original because there are four statements now, the four conditionals. The original conditional and the contrapositive. That's the last one, okay? The contrapositive are logically equivalent. So out of these four statements, the conditional, and then the converse, inverse, and contrapositive, the contrapositive is the only one that is still logically equivalent to the conditional statement, the original conditional statement. And then the other two, the converse and inverse, they are logically equivalent to each other, but not to the original conditional. Okay, does that make sense? Right. So it may be confusing. P implies Q, that's what we started with. All right. And if you switch the order, okay, so here, if you switch the order, then you get Q implies P, and that's called the converse. Okay. If you negate each, then you get the negation of Q, P implies the negation of Q, okay? And this is called what? The inverse, okay? Now, again, you have to remember or know these words. The converse is obtained by negating, by switching both. The inverse is obtained by negating both, but not switching the order. But if you do both, so negate and switch, then you get the negation of Q implies the negation, I didn't write that down correctly. This says the negation of Q. What happened to my pen? The negation of Q, you know what, let me just change my mode to, oh, something's happening here with my computer. All right, hold on a second. Okay, so here's, sorry for the sort of messy thing in the corner here, but basically what it says is if you start with the original statement, P implies Q, or if P then Q, then by negating each, you get the inverse. By switching the order, you get the converse, right? If you negate and switch, or switch and negate, you end up, either way, you end up with this thing called a contrapositive. Okay, and so here's the important part. The original conditional is only logically equivalent to the contrapositive. Okay, these are logically equivalent to each other. On the other hand, the converse is not equivalent to the original statement, and neither is the inverse, but they happens to be logically equivalent to each other. All right, so by going to the side or to the bottom, switching or negating, you don't get something logically equivalent. But by moving twice, okay, by switching and negating, or by negating and switching, you get something logically equivalent. Obviously, if you negate and negate, okay, if you go to way down here and here, next one, negate and negate, will get back to P implies Q. If you switch twice, you get back to P implies Q. So here's the point. Any movement to the right or to the bottom will give you something not logically equivalent. But if you move twice, sideways or vertically, you get the same thing back. Or if you go diagonally, by negating and switching, or switching and negating, you get the contrapositive, which is logically equivalent. Yeah, this is really confusing. I apologize for that, but that's the way it is. Okay, so the deductive argument is true, or we say sound, if each statement is true and the argument is valid. Okay, so we'll talk about the validity in a moment, but the word valid simply means it is logically correct. And so this only has to do with the form, not the meaning. Okay, so you may make some ridiculous statement, like say, all birds are plants or something. Okay, but if the argument is, that still can be valid if the form is correct. But of course, it's not sound. Okay, so I'll come back to this in a moment. So you check for validity using what we call a Venn diagram. Okay, these are a bunch of circles. Now, they are easy and they're extremely useful in analyzing arguments. And analyzing arguments is one of the fundamental things we will do. So we want to make sure that we understand this, okay? All right, so before you check, we go to the next page, and then we'll be talking about these sets of things, sets of objects with Venn diagram, okay? So that's what we'll be doing in the next part of this video lesson, all right? So at this point, I will stop and then you can go and watch the next segment.